Okay, good afternoon. So we have been talking a lot about total knee replacement, and now we move up to the hip. We're going to talk about biomechanics of total hip replacement, and we're going to talk specifically about what types of hip implants there are and what kind of biomechanical issues should be solved. So the most common reason for a total hip replacement is osteoarthritis. It's very similar to the knee. But in addition, we treat patients with fractures also with a total hip replacement. Okay? So this is an osteoarthritic patient. You can see here still the joint space. Yeah? But you could see here it's very sclerotic. There is no cartilage here anymore. Similar to what we've seen in the knee. Often there is also a leg shortening because it's worn away here. So that means that we need to do something. We also treat fractures, and this is often in elderly. You can see here a neck fracture. The surgeon needs to do something about that, and what shall he do? So we use then a total hip arthroplasty, which is an operative procedure in which the diseased and destroyed hip joint is resected and replaced with a new bearing. And the aim is to relieve pain, increase mobility, and correct the deformity. And it's often considered as the most significant breakthrough in surgery of the 20th century. It has been very successful. I show you now a video of how a surgery is done. This is an animation. And here it says an anterior minimal invasive surgical approach, because the surgeon can approach the hip from the anterior side, from the frontal side, from the side, or from the back. And the anterior approach is something rather new because it requires a smaller incision. Okay, so this is just a short video about that.
Lying flat on their back is 8 centimeters in length and avoids these anatomic structures that are pointed out in the course of the animation. Once the incision is made, soft tissue retractors are placed in front of and behind the femoral neck, facilitating exposure of the hip joint. A scalpel is used to create a release of the capsule, opening the joint and exposing the femoral head and the acetabulum. Here, a sharp-pointed retractor is placed on the anterior lip of the acetabulum, facilitating removal of the remaining bone spurs around the edge of the acetabulum and the diseased acetabular labrum. At this stage, the hip can either be resected in place or it can be dislocated prior to making a femoral neck cut. In this animation, we demonstrate dislocation of the hip prior to making the femoral neck cut. Once the head and neck have been appropriately exposed, the capsular release is completed, and an oscillating saw is brought into the surgical field in order to remove the diseased and arthritic femoral head. Here's an illustration of the oscillating saw making the neck cut in the proximal portion of the femur. The power corkscrew in the femoral head is then used to lever the femoral head out of the acetabulum. Soft tissue retractors are now placed about the acetabulum to facilitate acetabular exposure in preparation for acetabular reaming. In this step, an acetabular reamer is brought into the acetabular socket, and the remaining of the diseased osteoarthritic cartilage is removed prior to pressing in place the acetabular component, which grows solidly into the bone. A plastic bearing shell is snapped inside the acetabulum. The hip is then exposed by flexing the table and placing soft tissue retractors about the proximal portion of the femur, facilitating exposure of the proximal portion of the femur in preparation for femoral broaching. The soft tissues at the superior corner of the exposed femoral neck are released, and a rondure is used to remove any remaining residual neck. A series of cutting broaches are then impacted down the length of the femoral canal, preparing the femoral canal for final implant insertion. Once the final broach is in place, trowel components are assembled on top of the femoral broach, and the hip is put back in the socket, a process that we call reduction, in order to trial the fit of the components. At this stage of the operation, when using the direct anterior minimally invasive approach, it is also possible to examine the hip under fluoroscopy to make sure that the limb lengths are appropriately reconstructed and that the fit of the components within the anatomic landmarks of the acetabulum and the femur is appropriate. At this stage of the operation, we check to make sure that the final fit and fill of all the components is appropriate. The trowel components are exchanged for the final implants, and the hip is reduced and the incision closed up.
Okay. So basically the cartilage is affected, but still you ream out the acetabulum, you ream away the remaining cartilage, and on the femoral side you make the whole cavity, you make a complete cavity with a stem, whereas only the cartilage is basically worn away. So that's a little bit of a, you would almost say, an overkill. And people started to develop hip prosthesis by only replacing the cartilage. So for example, in this case, so in 1920, this is a little bit of history, people only replaced the acetabulum because you can see that the cartilage has worn away, so they only replaced the acetabulum. So here you can see all kinds of cups that they tried. And then they thought, we have to replace only the cartilage. Later on in 1936, people developed the lost wax casting methods. Okay, so we could cast implants, and we could cast implants with complex geometries. And then they developed, let's say, more the stemmed implants. Around 1945, the Joydeep brothers, these were brothers from France, they developed a plexiglass implant. You see here all kinds with a short stem. You see this is a short stem, and on top of that is plexiglass. And the plexiglass is basically the same constitution as the bone cement that we now currently use. And I have one of the Joydeep prosthesis with me. You can see it here. And I'm not sure, you cannot see the wear patterns on it, but you can imagine if this wears, this is quite hard. It's quite hard, so if these wear particles end up in your joint space, they will cause a problem. So they failed quite quickly. On the other hand, in our institute, I think some 10 years ago, we revised a patient with 2 Joydeep prostheses, and they had lasted for 54 years. And so they revised it with a normal stemmed prosthesis. So this is the Joydeep prosthesis, and this is afterwards. So although they failed in big quantities, in some patients they did very well. And that's also what we see. You know, some implants can be very successful in a typical or a specific category of patients. Okay, in 1938, McKee and Farrar developed this system, which was an all-metal system. So they had a metal cup and a metal head, and they connected it by means of this plate. Yeah. So this is a metal-on-metal bearing. This is Mr. McKee. And at that time, you could kind of pioneer and come up with different designs. And of course, we cannot afford it anymore because we have very good designs. So if you design something else, it has to be better than what currently is available. And that's not so easy anymore. And it takes many years to prove that. So they had only short-term success because they had problems with the cup fixation. And there were many patients with metal sensitivity, and especially there were high frictional torques. And this was due to the fact that this is a metal head articulating in a metal cup. And at that time, the manufacturing tolerances were not so good. So often they had a joint that was jamming, you know. And if it's jamming, it's basically loosening and wearing very quickly. So that's, yeah, that failed. So after that, in the 60s, Sir John Charley is a very famous orthopedic surgeon, and I think you should all remember his name, because he is the founder of the current cemented hip prosthesis. We call him the man of the hip. He's also written a book on that. So you see here a picture, and he's from Wrightington, from the UK, and he's being the inventor of low friction arthroplasty, which was metal on polyethylene. So that's why we use now polyethylene. So I have here a number of implants, and I think I can show you a little bit about that. So, for example, we have here a Freeman prosthesis. Can we have a top view, perhaps? So this is a Freeman prosthesis, and you can see that this is a cementless prosthesis, and usually the resection level of the cut that we also saw is around here. And Mr. Freeman thought, okay, if I keep this piece of bone, it's more stable. But you can imagine there was also a problem, because if this is articulating with a cup, it very quickly impinges with the cup, you know? So to retain this neck is very challenging, and it needs to requires a very accurate positioning of the components. But I think it's still in use. Okay, so that is the Freeman prosthesis. We also have the luminous prosthesis, which is one of the most successful cemented prostheses. So it's polished here, and there are some, it's a little bit roughened here. This is cemented. And here you see another cemented example, which is very smooth. It's polished. And we will see in the next presentation that I give, next lecture, that polishing of a cemented component might have its benefits. So it's a cemented implant. And this is another cemented implant, which is roughened on the top and polished at the distal side. This is the SHP prosthesis, which currently is not used anymore. This is an Exeter type of prosthesis, which is very popular, especially in the UK. And for example, in our institute, we also use it. So that is cemented. I have already shown this implant, which is covered by hydroxyapatite. And hydroxyapatite is the substance of it's calcium phosphate, and the bone likes that, and then it attaches. So this is a cementless implant, just like this one, which is very rough. It's made very rough, and that's also why it allows bone ingrowth and fixation. And this implant is less rough. This is a Zweimüller prosthesis, but it's still very successful. Okay, so you do not need a very high amount of roughness to make it stable. So I have some other things. That is, for example, this implant. Look at the difference. This is huge. And this is typically used in patients with a periprosthetic fracture at the tip. So suppose I have an implant and the bone fractures at the tip due to a fall. So I have a bone fracture here, and what the surgeon then does, he will take the prosthesis out. There is a bone fracture, and then he hammers in this nail. He passes he bypasses then the fracture and stabilizes the fracture with this large implant. This is really large. Yeah? Okay. I also have this implant, which has a very big head, and that's very different from this type of head. So this is an articulating. This is a total hip replacement, and this head is basically has an outer diameter which is as big as the acetabular component. This is typically used for elderly patients. If they have a fracture of the femur, you do not need to repair the acetabulum because the acetabulum is okay. But the most important thing for elderly patients is that the surgery is very challenging for these very old patients. So you have a very old patient, fracture, a hip fracture. Now it's very devastating and the condition of the patient is not good. So the primary aim of the surgeon will be to repair the fracture and get the surgery done as quickly as possible. So he will use then a hemiprosthesis. This is a hemiprosthesis, a one-sided prosthesis. And he will accept that this articulates on the cartilage of the person, of the acetabulum, which will wear, but the person is very old. These people are in a nursery home, so they will treat then the fracture, and they will accept that this articulates in the normal acetabulum, which is not optimal, but for these patients it is a good solution, and they have a shorter operating time and therefore a bigger chance to survive, basically. Okay, so what else do we have? We have here, so this is a polyethylene cup, and this will be cemented. It has these ribs here. So this is going to be cemented, and this, of course, you can imagine, is a hydroxyapatite coated cup, and this is very rough. This is cementless, okay? You have also cups that have a screw-in fixation. So this is basically has screw threads here, and the surgeon can just screw it in to fixate it. And there have been a number of designs of screw fixation cups, but most of them failed. There's only one type, the Zweimüller cup, which you can screw in, and that's quite successful. So it depends a bit on design again. And then I have here a very small prosthesis. So you could compare it to this one. Huh? I mean, this is very small. Huh? What do you think this is? Huh? Children? No, this is for a goat. Ah. This is for a goat study. Actually, this was also used, I've been told, for a very small Japanese patient also. But okay, that's of course very unusual. And this is for a dog. So you can see here, this is this is a rough coating, and you can imagine that if we design a new coating, we want to assess whether it is going to be successful. And then you can do an animal study, because you cannot do a finite element analysis to do that. I mean, it's a biological phenomenon. So we would then do a dog study. And of course, the dog biological environment in the dog is very different, but it's the best you can do. Okay, so I got you. Huh? So let's look at the hip replacement component. So we have an acetabular cup, and in the cup usually we have a polyethylene liner. We have a femoral head, which you can put on the neck, and then we have a stem. And there are a number of parameters that determine the size of the implant. So it's the medial offset. This is what we call the medial offset. Huh? So this can be smaller or larger. And this is important if the surgeon wants to reconstruct the anatomy. He will measure on the X-ray how much this should be, and then he will select the size of the implant. The same with the vertical height. So this is the resection level. Yeah, this is going to be the resection level, and this is the shoulder of the implant. So this is the shoulder of the implant. This is the shoulder, and it will rest on the bone. Okay. Okay, and then it says version of the femoral component. Version is the rotation relative to the bone. Okay, so the surgeon will assess how he should implant it. So should he implant it in this way or in a slightly rotated way? And I told you before, it is important that we are not symmetrical. The cup points forwards and there is version. It's about 10 to 15 degrees. And the anteversion is mentioned here, 10 to 15 degrees of anteversion, which means I rotate it 10 to 15 degrees. And that allows me to flex a lot before I hit the plastic. Okay? Because if I would do it otherwise, I cannot move a lot. So in extension, I cannot extend a lot, but I don't need to extend the hip a lot because it's only 10, 15 degrees. Okay? So this is an example of an X-ray of a patient that has a varus neck of 124 degrees. So the surgeon could draw an axis here, and this angle would be 124 degrees. You can also see that if he projects the implant shape, the center of rotation is here, whereas the center of rotation of the implant is here. So he cannot reconstruct the anatomical center. So he will choose for another geometry of implants, which has a smaller neck angle of 121 degrees, yeah, and with a bigger offset. So now he is in the right ballpark of choosing that implant. So this is called pre-planning based on an X-ray. So the surgeon will pre-plan on the X-ray what type of implant he needs. And if he can't find the good solution, he might look for another company and order another implant maybe. Okay, now there are all kinds of different types of components used with cement. I just showed you a few. So this is the luminous. This is another type, and this is the highly polished one. This is the Exeter one. And these implants come with different sizes. So the head sizes are from 22. This is the Charlie prosthesis, the man of the hip I just explained. He invented the implant with a very small diameter. But there are also implants with larger heads. And the indication or the incidence of dislocation is higher for smaller heads. And I can explain that perhaps. If this head is small, I will hit the boundary of the cup very quickly. If it's bigger, I can move around more. Okay? So the surgeon, in terms of stability and range of motion, would like to have a bigger head. But if you choose a bigger head, it means the plastic is thinner. And we cannot have very thin plastic. So there is a balance to be made. Okay, when John Charlie started, he used a neck diameter of 12.5 millimeters. So this is this neck diameter. Yeah. Currently, the materials are stronger, and now we have neck diameters of 10.5, for example. And that also means that I have a greater range of motion, because if this neck is thinner, I can move around more before the rim is hit. Okay? So I call this impingement if I hit it, and I call this luxation if through the leverage it's dislocating. Okay. Now we have a range of stems, and the main problem of cemented implants is mechanical loosening, and we will talk about that in the next lecture. So what about cementless fixation? Here you can see two implants with a proximal porous coating. It's more proximal because they want to reduce stress shielding. Huh? We know that now. And the basic principle of a cementless component is to provide bone ingrowth. And it is being used primarily for young and active patients with relatively good bone quality. Because if you put this implant in a very osteoporotic bone, then it will show too high micromotions. Now, there are two aims or two requirements for bone ingrowth. You need to have immediate stability. The micromotion should be not too big. And you also need to have good contact, because if there are big gaps, the bone cannot cross that gap. So the implants must be designed to fit the endosteal cavity that the surgeon makes with the reaming. It needs to be a nice fit. Okay, and there are two types of implants. So we've seen these implants already. I just showed you the picture, but if you look very carefully from the lateral sides, the side view, they are different. What is the difference? Exactly. One is straight. So this is symmetrical. Huh? This is purely symmetrical, and this is bent. You see that? And the bone actually is bent. So this is what we call an anatomical design, and this is a symmetrical design. So from left to right, you have a different design. So the surgeon should always take care what is on the prescription. Is this a left prosthesis or a right prosthesis? If it's symmetric, it doesn't matter. Yeah? And the idea is that this fits better with the curvature of the bone. I think that there are not many studies showing the real benefits, but the concept, of course, is logical. And the aim of both types is to provide an optimal fit, both proximally and distally, and thereby achieve axial and rotational stability. Okay. Now, there are various types of coatings. So proximally coated implants, we talked about that before. Extensive coated implants, like this one, this is really long, and this is also a typical implant that would be used if there is a problem in the revision to bypass a fracture or a very weak spot in the bone because of the removed implant. And stems with hydroxyapatite. This is the Korai, and this is, I think, the stem that the surgeon also uses that we met this morning. Okay, there are also modular designs. Modular designs are typically used for non-standard cases. So you can imagine that sometimes you have a cavity and the surgeon needs to kind of create their own implant to have the best fit. And that's then a modular design. And also, for example, in tumor surgery, here you can see again a tumor implant. Then they need to be flexible and design an implant almost on the table, on the operating table. Now, this is also an interesting design. This is a screw prosthesis. So this is one big screw, okay? And if you look at the survival, this is from the Norwegian National Register. So in Norway, all patients are registered if they get an operation. If they need a revision, it's also identified in the register, so they know exactly how long the prosthesis will last. So here you see the survival, we call it survival, of the right and left side of the patient. So I have here the left side. After 1 year, there is 100% survival, and then there is some failure. But there is 95% survival after 5 years. On the right side, it fails much earlier. So that's interesting. Why would that be? I give you a hint. The screw is only one-sided. Yeah. So the force in our joint is coming also a little bit from the front. So on the left side, it fastened the screw. On the right side, it loosened the screw. Yeah. So from a mechanical point of view, that is really a little bit naive, huh? But so I don't believe that this is on the market anymore, and I don't think that they also made a reversed copy because I think it was, I don't know, it disappeared. Okay, but I thought I'd show you because this is, of course, for a biomechanical engineer, this is, of course, very interesting to see. For the patient, of course, it's very dramatic. Okay, we look at acetabular components. And the acetabular components can have an outside diameter, which have to accommodate, of course, the diameter of the acetabulum of the patient. And there are three types of acetabular components: cemented, cementless, or sometimes custom-made implants. So this is a typical cemented cup. I have it here as well. And you can see here the adhesive. So you have to imagine that the surgeon makes the cavity in the acetabulum and then puts in cement, which is a kind of a paste, and then he puts in the implant. Okay, and the bone cement polyethylene adherence strength is not so high. If you make it smooth, you can take it all out almost immediately. So that's why there are all kinds of ridges in it to grab hold of the cement. Okay. What you also see here is these plastic spacers, and they make sure that if the surgeon pushes in the implant, the spacers are resting against the bone, and will make sure that there is always a gap remained between the plastic and the bone. So there is always a cement layer, because otherwise he would push away all the cement, okay, if he pushes it. So these are called cement spacers, which makes sure that there is a cement layer around the plastic component. You see here also there is a metal ring. The metal ring is used to be able to see it on an X-ray, because we cannot see the plastic. So I have also here, this is with a metal ring, because this morning we also saw that there was a dislocation of the knee. Remember that? And we couldn't see the plastic very well. If this is going to loosen in the acetabulum, you want to know whether it's loose or not. So you need to be able to see something of the component, and that's why they have the metal ring. Okay? Okay, so there are also cementless acetabular components, and they are provided with this coating, and then the plastic liner is inside. The advantage of this is that if the coating is very successful, the implant will grow very, very well in the acetabulum. And if the plastic then wears out, the surgeon can click out the plastic and replace it with a new one. So it's kind of, you know, having your car done. So, so it's kind of, it makes sure that we can exchange the plastic cup. We only do that, of course, if the ingrowth is very well. Okay, we can improve the initial stability of these cups with spikes or with screws. There's some surgeons would like to use that, and especially in compromised cases like osteoporotic patients. Okay, so there you can have a screw or spikes, or you can have a press fit, like the interference fit that we talked about this morning on knees. This also goes for cups. So the surgeon will make a hole which is smaller than the cup, and then it's nicely press fitted. This is an example of a cementless cup, which is, I think, still experimental. So what the surgeon will do is he will deform this cup so it has a smaller diameter, put it in, and then release it. And with these spikes, it fastens itself then. Okay, so if something goes wrong, you can have a dislocation, as I told you. And dislocation can be due to wrong placement. So, for example, if I do not place the components to the front and I place it symmetrically, you can imagine that there is going to be a luxation. It can also be due to the combination with a very small head size, because then it's more sensitive to dislocation. There can also be the laxity of the soft tissues can be too low. That means that there is a capsule around the joint which keeps the joint together. If the laxity is not enough, there is too much play here, and in a certain event, it can pop out. You know, so the surgeon has to make sure that there is enough tension in the capsule, and that's also due to an insufficient offset. Because if the neck length, if this is shorter, the capsule will be less tensed And therefore, you run the risk that it's also easily popping out. And what they do is they first try to reduce the joint. So that means they put it back and then they kind of hope for the best, or do a reoperation. But this is this usually happens very early after the operation, and the surgeons don't like it because they made a mistake. Often, it's not. Okay, so optimum positioning of the prosthetic socket is important to prevent that luxation. I think you got the message. So there is an area of inclination, that is this angle, inclination, and anteversion that the surgeon needs to hit for the most optimal placement and the least chance of dislocation. We talked about the neck diameter, so this is the ball, and this is then the neck diameter. And here it is very clear that if you decrease the neck diameter, you can have a larger range of motion before you hit the plastic. It's very logical, huh? But of course, we have to take care that the neck remains strong enough. So we have to remain careful. So here you see an example of a cup that is put in very vertical. And you can imagine if the tension of the capsule is not good, it can pop out very easily in this case. Sometimes when they put the cup in too medially, you can have bony impingement, bone-to-bone impingement. And we used to not look at that, but sometimes we see now that impingement is also on the bone. So what happens then, if the patient is moving the leg further, this pops out because it's resting here and it's dislocating. Okay, so you think that there is something wrong with the joint, but actually there is impingement on the bone, on the bony parts. And now with modern computer simulations, we can make CT scans. We can actually simulate that. Okay, the coefficient of friction is of course very important, and friction is the measure of the resistance encountered in moving objects. I think most of you will know that. And the coefficient of friction for a normal joint is extremely low. It's lubricated. We talked about cartilage. It's really very low. The coefficient of friction of metal on metal is a little bit uncertain. It depends on the lubrication. And we will talk about that in a minute. The coefficient of friction of metal on polyethylene is also quite low. And that's why this joint is still kind of the standard. But we haven't been able to generate a joint that has a coefficient of friction as low as the natural joint. Maybe that's a challenge for you. Okay, so sometimes these joints can jam. So suppose that I have a metal-on-metal component and it's really jamming. Okay, so the advantage of poly on metal is that it never jams because it's soft. It doesn't jam. But metal on metal could jam. If you have then a small diameter, you can imagine that the torque on the outside of the cup, on the cement layer, is relatively low. If you have a very big ball that is jamming and the patient is moving the leg, it's going to generate a very big torque on the fixation. So here you see the head, the polyethylene, or the cup, I should say, and this is then the cement. If you have a small head, the stresses on the interface will be lower than if you have a big head causing that jamming. And what we see now, every now and then, is that we see now loosening of cups, especially with big balls. If you have a non-very well articulating metal-on-metal cup, it's loosening at the cement bone interface because of the big forces. Okay, so we have alternative bearings nowadays because we know that polyethylene wears. It does wear. It's a very nice material, but it does wear, as we've seen before. So we can have metal-on-metal bearings, ceramic on ceramic, ceramic on polyethylene, and we have invented a better cross-linked polyethylene, a better plastic. Okay, Metal-on-metal implants are very tolerant against impact loading because they are very strong. But the tolerances need to be made very tight. As I explained with the McKee-Farrar prosthesis, the tolerances were not good and it was jamming all the time. So we need to make it very good. And there is, however, a major concern about the wear particles of cobalt and chromium in the joint. Okay, so it is a strong material, it doesn't wear, and it's been used for dancers and athletes, these metal-on-metal bearings, who would like to be very mobile and require a high stability. For example, dancers, they need a very big range of motion. Huh? For a very big range of motion, you need a big head. So you see here, this is the head. Look at this size. It's almost this size. And the metal cup doesn't need to be as thick as the polyethylene cup because the metal is much stronger, so the head can be bigger. So that's why there is a bigger range of motion with these metal-on-metal implants, like you see here. So that's why they kind of implant it in athletes and dancers. The disadvantage is, however, the wear particles. It's not a large volume of wear particles, but the wear particles that we get are perhaps toxic. That's why they would never put it in pregnant women or women who expect to have babies, or people have kidney problems. And the problem is so big that they currently ban it in some countries. So in some countries they say you should not use metal-on-metal articulation because we do not know how toxic these metal particles are. So there is a lot of discussion now, and I show you here an MRI scan of tissue that is basically, it's kind of an inflammation. So this is a response to the metal particles, and we call it pseudotumors. And the interesting thing is that you do not see that on an X-ray because it has nothing to do with bone, but the soft tissues, your muscles, they dissolve a bit. So before we knew this, it was years after the introduction of metal-on-metal. So there are a lot of people walking around with metal-on-metal implants that are in danger of having very weak muscles and soft tissues. The pseudotumor, the tumor is not, it's not a life-threatening thing. It is only kind of the dissolvement of the soft tissues. Okay, and this is a picture of a registry. So we see here the failure rate against the number of years post-operatively. And we look at ceramic on ceramic in green, doing very well. We look at metal with new polyethylene, doing very well. But if we look at metal on metal, we see that the failure rate is much higher. So that is why in many countries they said, well, you know, let's wait and see how it develops. So it is problematic. Metal on metal is problematic. Okay, what about ceramic on ceramic? You can see here a ceramic ball articulating in a ceramic cup. And the cup is embedded in a metal backing, and the metal is provided with a rough surface. So there is a ingrowth surface, and there is ceramic on ceramic articulation. These implants are usually quite expensive because they need to be made very accurately. But ceramic on ceramic is a very well articulating and very hard material, but it's also a little bit brittle. But it's a very good bearing surface. And it wears 4,000 times less than cobalt chrome on polyethylene, and then a metal on polyethylene. So it doesn't wear so much. So this is how it looks like. Huh? And it's also being used for the younger patients. You can see that the head size cannot be as big as the metal on metal because you have first to have a ceramic layer and then a metal layer. So the head size is limited. However, there are some problems with ceramic. I mean, if I do this, we worried that this would, you know, get squashed. And that happened also. So here you can see an X-ray of a femoral head that has gone away, basically. So you can see here in surgery, you have all these fragments, which is quite devastating, of course, and of course the device has to be revised, and it's really very problematic. Nowadays we have better ceramics which are tougher, so I think it's going in the good direction, but it's still quite an expensive joint, and I think a lot of orthopedic surgeons will not choose that option because of it's very costly. Okay, one of the interesting things also is that sometimes patients complain of a squeaking sound. Okay, and I have a movie of that, what I thought was nice.
Right.
Nice, huh? Not for him, but
You just keep going.
so he walks perfectly happy, but the joint is not lubricated. Eh? I mean, it's ceramic on ceramic. So yeah, so that is really a problem, and they have figured out that in some designs, these designs are more sensitive for squeaking than other designs. But you can imagine, at first there was a hype on ceramic. It was all great, and then suddenly the patients came back because this can be very annoying. I mean, if you walk on the streets and everybody looks at you, or you know, so okay. So we go back to polyethylene wear because that's kind of the standard, and we need to reduce the number of wear particles because the wear particles, they can lead to osteolysis, and it means that there is a lot of bone loss around the implant. It gives irritation, it gives pain, decreased mobility, and it can lead to joint failure. And aseptic loosening of these implants due to wear debris is induced by osteolysis and has been identified as the leading cause of late failure in total hip arthroplasty. So we really need to do something about it, and that's also why companies design these other bearing alternatives. So this is how it looks like. So you can see that the head is not in the center of the cup, right? And that means there is wear. Yeah, and it means, and what you then typically see is that there is a dissolvement of bone here, and especially, so you have to imagine that there are a lot of wear particles floating around here, and they can escape through the screw holes also. So we often see around screw holes. So it doesn't have to contain a screw, because sometimes a cup have multiple screw holes to facilitate the surgeon, and he opts not to use them. So there is an opening to the acetabulum, and around screw holes, we often see then that the wear particles accumulate and cause osteolysis. And of course, when this goes on, it could loosen, or when the patient has a fall, it can break out the cup. So osteolysis is really not good. It can be even, osteolysis can also happen more distally. So what you can imagine is that if you have particles in the joint space, they can migrate along the interface between the cement and the bone, because there is always some movement and some fluid flow while walking, and the particles go down, and it leads to osteolysis. So they open up that interface, and they move down and down and down and down. So that could also lead to loosening of the whole femoral components. And especially, so we talked the day before yesterday about that white band. Do you remember that, for the radiation? In the cups, that's also true. So here you can see that subsurface, you have a weakening of the components. So you can imagine if this wears, it wears, and it reaches this level, it suddenly wears a lot because it's weaker, okay? So we have dealt with this because of new irradiation methods, new polyethylenes, but osteolysis is still a problem, although we have reduced the number of particles a lot. Okay, so not only the wear particles cause osteolysis, but also they cause that the joint cannot move anymore, because you can imagine if it's so close to the metal backing, you can have, you know, the mobility is gone. Huh? Okay, so then you need to have a revision surgery. And of course there is added costs, it's difficult to recover, people lose faith in the procedure, and the survival of these revision cases is not as good as the first case, because the bone quality is compromised, everything is compromised. So the revision, you should avoid revision. That's why we seek for a lifetime solution. So people develop new polyethylenes and they test it in machines. And this is a hip simulator of AMTI. It's an American company. And they have the same kinematics as the hip. Of course, it's prescribed, so it's not as variable as we would use a hip. But nevertheless, they do a lot of testing on these new polyethylenes that people develop. Okay. And what you see then typically is that first the cup is wearing very quickly, and then there is a steady state. The steady state is about 0.1 millimeter per year, but now with the new plastics it's less. But it used to be 100 microns per year of penetration depth. So you can imagine that you can measure that. So so this was the machine, huh? You can hardly see the components, but you can take out the component and measure how much wear there is. You can imagine that. On an X-ray, it's much more difficult. So the people measure then how much the femoral head is penetrating into the plastic. Yeah, so you can see clearly here that it's not in the middle anymore, here also. And so on the annual review, when the surgeon makes the X-ray, they're going to assess how much it is increased. So virtually all companies have been working on improving their polyethylene to get rid of the osteolysis. So there are many things that you can tell about, and I also don't understand a lot about it. So this is a slide of all the companies: Biomet, BioPro, Corin, Dept, another polyethylene of Dept, Meritin from Dept, Encore, Endotech, Exactech. So these all have different ways of treating polyethylene and sterilizing and packaging it to make sure that we get rid of that oxidation that we talked earlier about, and to reduce the wear rates. And they can show that on these hip simulators. So I just show you an example how that works out in patients. So in '96, so almost 20 years ago already, Stryker introduced Duration. That's a new polyethylene. This is the treatment they do, and people did a clinical study, and they compared it with historical polyethylene and the new polyethylene. And you can see here the wear rate, which is the head penetration, and they measure on X-rays. And you can see that the duration is less than the traditional one. But the gain is not huge. But nevertheless, it is better. So, you know, it's a gain. We have to work in small steps. When we look at osteolysis, somebody did an extensive review and reviewed all new polyethylenes that had been introduced in the market and clinically tested. So these are all publications on the comparison of old polyethylene and new polyethylene. And what you can see is if it's one, it is the same. If it's less, the new polyethylene wins. So you can see that in all papers, the new polyethylene is more successful. So that is very, very good. And in fact, in terms of osteolysis, so the effect on bone resorption, it is 87% lower risk. So that is really very good news. And I think we have now enough proof to use highly cross-linked polyethylene. Okay, so we had ultra-high molecular weight polyethylene, and now we have highly cross-linked, ultra-high molecular weight polyethylene. So in a very large study in Australia, they also have a register. They keep track of all the patients who are operated and who are revised. And they have done that with non-modified polyethylene and with this modified polyethylene. And you can see that the modified polyethylene does better. So this is the percentage of revision again after years. So after 9 years, we have almost 2% of revision gained. So in very large cohorts, these could be maybe 20, 30,000 patients. We see the benefit of these highly cross-linked, newly highly cross-linked polyethylenes. Okay, the last bit of this presentation is about forces around the hip, because we are biomechanical engineers. And I thought this is very simple, but I think it's still interesting. So if you see this hip joint and your weight is applied here, it will rotate around the hip center and it will collapse immediately if your muscles would not pull it back. Okay, so if my weight would be 750 newtons, so 75 kilos here, my muscles have to pull back to keep me upstanding, yeah? Because this is the center of rotation. We see that the distance here is larger than this distance, so the muscle moment arms are quite small around this rotating center. Let's say it's about half. That means that the muscles have to pull back 1500 newtons, double this force, because the moment arms is half. And we have to have equilibrium. Okay? So that means that the muscles pull my hip joint together and my weight. So this is then 3 times body weight. Okay? So the hip contact force is determined primarily by the muscles and to a lesser extent by the body weight. So if I would ask that to surgeons, the surgeon would say, oh yeah, the force on your hip joint is 750 newtons because that's your weight. But it's more complex than that. It's 3 times body weight. Yeah. Okay, so how do we know that is right? Well, people have developed in Berlin sensors to measure forces. And we talked a little bit about that with some of you. So this is work of Georg Bergmann. He deserves maybe the biomechanical Nobel Prize for this, I would say. So because what he did is he instrumented strain gauges, we talked about that before, in the neck of the implant. And if there is a high force on the implant, the strain gauges will pick it up. And then if you have calibrated it before, we know how much force there is on the implant. Okay, so this is a movie, and you see here a patient walking around, and we will see how his forces are changing. So he's walking here. He's talking or something, I don't know. Yeah. So what we see here is that during walking, it is a little bit over 2 times body weight, 200% of body weight. Okay. What you can also see is this direction, is that it comes slightly from the front. So that is important with the screw prosthesis I just showed you. This is mild, but if you do a stair climbing, for example, it comes more from the front. Okay, so this is how we know and how we measure the hip joint forces. This is another case. And you see here in this video, you see the back view and you see the side view of this. This is the patient, and he's going to walk up these stairs. Okay, let's see what he does. So here comes here. Oops, you saw he was stumbling. Okay, I run it again. Let's see. Oop. Yeah, so he's stumbling. And what it means in the hip contact forces is, so he's walking up the stairs and he's stumbling here, it's 7 times body weight, 7 times body weight. Whereas if we do tests on hip implants to do the fatigue testing, I think it's 3 times body weight, something like that. So you can imagine that due to such a small, it's a mild stumble, right? So if people fall, then you could break a prosthesis. So there is a lot of debate now about increasing the standards of testing. Okay, so what I found is, it's a very busy table, but these are different patients in which they had an instrumented hip prosthesis. So for walking fast, it is about, let's say, almost 3 times, 2.5, 3 times body weight. For stairs down, it is a little bit similar, but maybe a little bit higher, 3 times body weight. And for stumbling, they found another incidence of 8.7 times body weight. And if you do biomechanical modeling or testing, we use this data all the time. But I'm not sure sometimes whether I should do walking or whether I should simulate stumbling. I mean, what is now jeopardizing the fixation of an implant? Huh? That's not so trivial. Now, one interesting aspect is that the surgeon has to choose the offset. Okay, so he can choose a femoral component with a big offset or a small offset, as we've seen before in that example. Thereby, he changes this D, the offset of the abductor muscles. So if he uses a small offset, the muscles have to pull harder. If he uses a bigger offset, this becomes more effective. Okay. So if he uses a small offset, the stresses will increase, or the forces will increase, and thereby the stresses on the polyethylene, I would guess. And there's one interesting study that studies in 17 patients the wear of prosthesis, and the patients have prosthesis on both sides. And on one side they did a large offset, and the other one they did a small offset. So it's an intra-patient comparison. And what they showed is that the standard offset has 0.21 millimeters per year wear, and the lateral offset, so the bigger offset, the more effective for the abductor muscles, had half of that wear. So that shows to me that there is maybe a relationship between the force applied and the wear rate. Of course, it's a little bit speculation, but when I saw this paper, I had to think about that. This is, I think, rather interesting. Okay, so this is my last slide of this lecture. It shows the Swedish register, results of the Swedish register, and the Swedish register is the oldest register that we have. It started in '79 already. And what we see here is the percentage non-revised components. And after 20 years, we see a survival of, let's say, 65%. This is the survival of patients younger than 50 years. So for young patients, we have 65% after 20 years, and that is not good enough. For older patients, it will run, we have a solution. But for the younger patients, we need better solutions, and maybe that is something that you all can work on. Thank you very much. Yeah, I mean. Okay, good afternoon. This lecture is about cemented total hip replacement and the research that we have been doing over the last maybe 20 years. Actually, I did my PhD on this topic. So, cemented total hip replacement means that the components are fixated with cement. So you see here the components, and the green is the cement, okay? And during surgery, the surgeon will try to impregnate the bone with that cement, which is still in a paste phase, and he can use a syringe to inject the cement. Okay, so he's going to inject from here to here, then pressurize it so that it penetrates into the bone. He waits for a little while until it hardens, it polymerizes, and then he puts in the stem. And during this talk, we're going to look at the femoral component only. Okay, so what do we have? Here we have the cement layer around the stem. Here we also have the cement layer, and we're going to look at three interfaces, or three. So this is the stem cement interface. This is the cement layer itself, and we're going to look for a very quick tour to the cement bone interface from a biomechanical point of view. First, the stem cement interface. So you can do a lot of testing and you can make this implant rough and then check what the push out force is between the stem and the cement. Okay, so if you increase the roughness, you increase also the load. That's not a surprise. Huh? So the rougher the stem, the stronger the interface. People have published that a long time ago. So we should make it rough to make it strong. However, if you look at migration studies, and this is a study from Sweden, and they can look very accurately to the migration of the stem in the cement. Okay, so you see here the migration of the stem in time. So this is 24 months. You see the migration of the stem in time. What you see is that they all migrate. So it means that they move in the cement mantle, and it means that they debond from the cement. So there is movement, okay? So migration studies show migration of most stems, and that means that the stems debond from the cement mantle. So you could say the rougher the stem, the stronger the interface, but apparently, clinically, that bonding strength is not good enough, okay? So people have looked at retrievals, and here you see a section of a retrieval with here the prosthesis, here the cement, and here the interface. And you can see that's clearly loose. There's not a lot of gap or so, but it's certainly not really fixated. You can imagine if you make this then rough and it debonds, it could have a rasping effect, and that's kind of what I'm going to demonstrate. Okay, so we have looked at this using finite element models, and we can calculate with these finite element models stresses and strains. We can simulate cement creep, cement fracturing, and we can look at how stem cement debonding, what we just demonstrated, that clinically actually happens, how that all works together. So if we calculate the stresses between the implants and the cement, we can calculate where it will start to debond. That's where the highest shear is or the highest tension. And typically it starts at the tip and on the proximal side. And then if this is debonded, the stress peaks go up here, and this debonded region grows until the whole implant is debonded. Okay? So debonding generally starts at the tip and at the resection level. Okay, so if you know that, perhaps you can strengthen the bonds there where you expect debonding. So people have provided the implant with a pre-coating. So this is manufactured with a bone cement layer, which is very strong on the top and on the bottom. Yeah. to make sure that that's where the bonding starts, they make it stronger. What you can also see, by the way, is these white dots. Where do you think they are for? Huh? No, they are resting against the bone, but these are again cement spacers. So they make sure that there is a cement layer between the metal and the bone again. It's very similar to the cement spacers on the cup. Because it could, otherwise it could be if the surgeon brings in the prosthesis, he shifts it against the bone and there is no cement at all. So he needs to have a kind of a sliding system, and the spacers will take care of that. Most stems do not have that, by the way, but this stem happens to have that. Okay, or so you strengthen here where you expect debonding, or you can accept that debonding is unavoidable and then polish the stem. We talked about that a little bit before. So what happens in debonding or bonding? So if you have a bonded interface, you can have compression transferred, you can have tension transferred because it's glued together, it's bonded, and you can have shear stresses transferred because it's glued together. In the unbonded condition, you can have compression, but you can also have tension because, like the gap, it just opens up if there is tension, so there is no tension. And there is some shear depending on the friction, because even the polished surface has some tension, has some friction coefficient. Okay, so for the surgeons, they were very scared when we talked about debonding because they thought debonding, it means that my implant is loose. That's not the case at all. You can imagine that this does not stick to the cement, but if it's embedded in the cement, it can be very stable, right? Because it's completely surrounded by hardened bone cement, and it does actually very well. So clinically, we know that. Okay, so debonding is not grossly loose. Stems can be stuck in the cement mantle due to friction and remaining compressive stresses, because this is usually a taper shaped. So it very slowly subsides, and it stresses the cement every time, when it subsides a bit. Okay, so we're going to look at debonding of cemented stems, and I have here this sketch. So if there is bonding and you load a stem, there's going to be a lot of shear stress between the implant and the cement. Okay, if it's too high, it's going to debond. That's what we see clinically. Yeah? Let's say we polish it, and we polish it super, there's no friction at all, it means that the implant will subside a lot and is then kept in a position because there is so much compression that it cannot be further, because before it completely splits the cement mantle. So you can see that there is a kind of an expansion of the bone and the cement. Yeah, this is a cross section, huh? And there is huge compressive stress, and that compensates for this axial force. In reality, there is quite some friction, even in the polished case. So there will be shear, and the shear stresses are very effective to balance this external load. So the subsidence will be less than in a frictionless case, which this is, of course, very theoretical. Okay? But nevertheless, it will have an expansive effect. So there will be, it will expand the cement mantle while it is migrating. So debonding has a splitting effect on the cement mantle. You can imagine if this is forced lower and lower, it will crack the cement. It will open up the cement. Oh. So if there is a splitting effect of such a component, why wouldn't you make it rough? Well, because then you increase the friction and then there is less migration. If we make it rough, it will cause abrasion. You can imagine that, because it will, by dynamic loading, it will abrade the cement mantle. And we have demonstrated that. So we have here a cement mantle, we have a polished implant, and we're going to load it dynamically for many cycles, 1.7 million loading cycles. Okay, and we have different roughnesses. So this is the cement, and this is the stem, and this is the interface. After 1.7 million loading cycles, we couldn't see anything if we make it super polished. And the polishing is exactly like this. So although we saw some subsidence, it is doing nothing to the cement mantle. If we make it very rough, it maybe, you know, it created a lot of wear particles and abrasion. You can see that these particles could enter into the bone and then cause osteolysis, and that's not what we want. So, I skipped a slide. Oh, I'm missing a slide. Okay. So we made a finite element model of that. So here you can see the taper, and here the cement, and we zoomed in to analyze the surface roughness. Yeah. So here it is super smooth, and here it is super rough. And if you look at the stress levels, at 5 micron roughness, you could see stress levels going up. If you look at 15 microns, stress levels went further up. But if you make it rougher, the stress levels went down. So here you can see that curve. So if we make it super smooth, stress levels were down, and we also see that in our test. If we make it a little bit matte, so this roughness, we see small particles. If we had 11 microns, we see very high local stresses. We see also abrasion. And in our finite element model, if we make it rougher, we didn't see high stresses. And I can explain that because if you make it super smooth, it's going to slide along each other. There's no damage. If you make it rougher, it's gonna abrade. If you make it even rougher, it will not move anymore. So you have a macroscopic interlock. And currently there are no implants on the market that have this. I'm not even sure why that is, but the companies do not believe in it. So most surgeons believe in highly polished implants, and they don't want to take the risk to make it really very rough. When we looked at the migration, we saw that the migration of the rough taper was less than the polished taper. So that means, although the polished taper had a bigger migration, bigger subsidence, there was less damage. Yeah. So it means that a rough taper generates more damage, and it means that migration is not related to damage. Whereas a surgeon would see on his X-ray, oh, it has migrated a lot. I think there is going to be a lot of cement damage, but it depends on the surface roughness, as we see here. Also, interestingly, you could see that the polished taper subsided in a stepwise fashion. It didn't, we expected that it would just gradually subside, but it's subsiding in a stepwise fashion. And for a bioengineer, that's very interesting, because what's happening here? Initially, I thought that we had a power, that the power switch was turned on and off, and that the machine was having a little bit of a problem. That happens in Holland too, but that was not the case. So what we did is, in the finite element model, we could understand that, because it's due to stick-slip. So for the bioengineers, this is maybe interesting, and for maybe the medical students, it's very complex. But you have to imagine that there is some friction here between the stem, and the cement, but it's in sticking mode. Subsequently, we have high stresses here in the cement at the tip, and we include creep. So due to the high stresses, the cement, let's say, goes away, and at the tip, we see movement, we see slip every time. And because it's slipping there, high stresses go up here. Because of the creep, so the slipping part is going to increase. So first we have slip at the tip, and then the slipping is increasing until everything is in slipping mode, But if everything is in slipping mode, zoop, it subsides again until it fastens itself. Okay, so that is what's happening here. So this is in complete slipping mode, and then it migrates. So then it whoop, migrates. So it was very interesting that we could simulate that. And I think also a stem will subside in a stick-slip fashion. And of course, the loads are very variable, so it's more difficult than in our situation where we loaded with a machine and we had a very nice stick-slip phenomenon. Okay, so it's clearly that these rough stems abrade the cement mantle. And clinically, we also have shown that. So this is an Exeter polished stem, which is a lookalike of this. Yeah, it looks like this. But later on, the Haumedica, which was the company, they thought, well, polished is not so good because it will debond quickly from the cement mantle. Let's make it a little bit rougher. And so they made a matte version. Yeah, and you can see here in blue, this is the survival of the matte stem. Let's say after 10 years, we have, what does it say? This is 90, so it's about, let's say, 85%. And here clearly the blue line is more on top. So the survival of the polished stem is better than the matte stem. So this was the early start. Then they started with an Exeter matte, which did not do so well. And they quickly reversed it to a polished again. So now, if you buy an Exeter implant, it's very highly polished. Yeah, and the roughness of an Exeter matte is exactly what we tested also. There have been other studies of a polished stem versus a matte stem, and they look at osteolysis, because we think that cement fracturing is associated with osteolysis, and you can see that on an X-ray. So for the rough finish, they had 47 regions with osteolysis, and with the satin finish or the more polished version, only 8. So they abandoned the rough finish. And this is another study in which they had 244 stems, grit blasted, so let's say rough, and polished stems after 55 years. And they had 6 pending failures for osteolysis. So 6 patients need to have a revision of the grit blasted group and no for the polished stems. So polished stems are really, that's a proven concept. Another aspect maybe of polished stems that could be very important is the fluid flow. And I will show you that. So this is an X-ray that we have seen before with the osteolysis, remember that? So you have to imagine that there are wear particles here due to the polyethylene wear. And if the wear particles want to move around, they want to move around where there is fluid flow. And if there is space between the implant and the cement, they're gonna travel around the stem, between the stem-cement interface, and they could get out, for example, here, if there is a cement fracture. Yeah, they could travel that distance, and then they can resolve bone. They can lead to osteolysis distal, at the distal site where the wear particles are formed. In this study, the authors show that if you have a polished stem, this will not occur, because a polished stem in cement closes, it's a tight fit. You know, if you make it very rough, there is space between the implant and the stem, and there is going to be fluid flow, and the wear particles can travel all the way. And if then there is a cement fracture, they can travel to the bone, and then they lead to osteolysis locally. Okay, so polished tapers close off the stem-cement interface. That is what it's like a stopper on a bottle, you know? So they looked at the fluid flow along the stem-cement interface, and what you see is if you make it polished, there is no fluid flow. If you make it rough, there is fluid flow. So it's a very, very nice demonstration that if you have you can have transportation of wear particles which could lead to osteolysis. In fact, when we looked at our specimens, so this is a cement, this is the taper, and this is a rough taper. This is an unloaded specimen. So this is nicely glued together, cemented, but you can already see that there is space between the cement and the taper. So even in the unloaded situation, you could have almost transport of fluid. So that might be an aspect that has been kind of ignored and may be very important for some patients. Okay, we're going to look at the cement material. We looked at the stem cement interface. We're going to now look at the cement material. And if a stem debonds, we will elevate the cement stresses because of that splitting effect. And because we talked about that earlier, if the stem migrates, it's gonna create circumferential stresses. And that's shown here. So the diameter of the stem is going to increase due to subsidence, right? It's going to compress the cement aside. Yeah, there's going to be circumferential stresses, and then if the stresses are too high, it's going to create cracks in the cement, typically around the corners of the stem, because there's a stress intensity. Yeah, and you can see that if you look at retrievals. So these are patients who have died and they were doing well, you know. So, but we look at how their implants look like. So you can first see that this implant is loosened relative to the cement, and there is a gap. And the gap is there because there is a crack here, and then the cement mantle opens up and facilitates toggling of the stem, and the stem becomes a little bit unstable. And you can imagine that there's also fluid flow between from the top to the bottom. So there is a crack, like in my previous picture, at the corner of the stem, and that's not a surprise because the compression generates tension, and then there is a crack. Okay, so if you look at autopsy retrievals, it can look like this. So what I've done here is I have removed the stem, and I look down with an arthroscopic camera, very small camera, inside the cement mantle, and you can see around the corners of the stem these cracks. And of course, that's not good news. I mean, we want to have an intact cement mantle. And that's also why I think that cementless implants become more popular, because this will happen. If you cannot expect from a cement mantle to last a lifetime. So if you have biological fixation, we can, I think, make it happen in the future. Now, this is a revision case, and we also used a camera, and you can see these cracks. It's very clear that it's around the corners of the stem. So we want to predict whether the crack is going to occur and in which situations that happens. So we developed a finite element model, which looks like this, very simple. It's just one slab. And we're going to calculate the stress intensity around the corner of the stem, and we can simulate the crack formation here. Yeah. And in Syracuse, we work together with people in America. They've done the testing, and it looks really very nicely. There's a nice fit, and we could also tune the time properties of this simulation. Okay, then we said, okay, let's dynamically load the implants in a sawbone because we can standardize that. So this is an MTS machine loading an implant which is cemented in a sawbone, and we tested two types of implants, a luminous and a Mueller curve stem. Just two types of implants, okay? And then we cross-sectioned it, and we looked at, after loading, how they look like. So here you can see the cortex of the sawbone, here the foam, and here the cement mantle. And what you can see in the luminous, you cannot see any cracks. And in the Mueller curve stem, you can see the cracks around the sharp corners. You see that? This is called the Mueller curve stem. And Mueller curve stem is not on the market anymore because it was not doing so well. And we think one of the reasons is this. So we exactly mimicked the experiment with finite element models, and we simulated the crack formation. And we had a nice prediction of the cracks here and here. We have cracks. We predict a crack here, which we couldn't find here, but it looks very nice and very comparable. And in the luminous, the very good performing stem, we also didn't find any cracks, so that was good. Then we said, okay, from that Swedish register that I talked about before, we know which stem is doing well. So the Mueller curve stem, this is the failure curve. The Mueller curve stem isn't doing so well. The Charnley of Sir John Charnley, the man of the hip, his implant is doing rather well. And we have the luminous and the Exeter, they do quite well. You can see here the failure rates after 10 years. So this is the champion and this is the worst. Yeah. And we made finite element models of these implants. And we used the loading conditions of the people from Berlin that I just showed you the video of the telemetric hip. They also developed proposed hip loads in the literature. Okay, and we predicted the number of cracks in the cement. So here we have the Mueller curve stem generating a lot of cracks, and that complies with the failure rate that we see clinically. And we see here the implants that we predict to produce a lower number of cracks, and they do clinically also well. So our simulation seems to be related to maybe the clinical performance, although we know that cement cracking is not the only failure mechanism. There are so many other things, but maybe we were a little bit lucky. But I'm sure that the Mueller curve stem is failing because of cement failure. Okay. Okay. Cement is a viscoelastic material. It's like plexiglass. And especially in 37 degrees and in a watery environment, it creeps. So what about creep and stress relaxation of this cement around these cemented stems? Okay, we expect that cement stresses are reduced because there is stress relaxation. But if there is stress relaxation, the implant can migrate. So that's what we expect. So I've shown you a little bit about this before. So if we have a piece of bone cement and we deform it, we put a weight on it, there is immediate elastic deformation, but if we wait for a longer period of time, it elongates. That is viscoelastic behavior. It's called creep. And stress relaxation is, okay, we deform it with a certain percentage. There's high stress, that's why it's red. If we wait, stresses are reduced, that's why it's orange. Stress relaxation. So we apply that to our finite element model, and then we can see this is the average stress in the cement mantle of a bonded or an unbonded implant, and we see stress relaxation in both cases. And it's interesting because the people who sold the Exeter stem, they said stress relaxation only occurs around the polished stem and not in a bonded stem. So, you know, you have to buy a polished stem. But it happens, of course, stress relaxation is a phenomenon of the cement. It's not bound to a bonded or an unbonded interface, or it happens always. Okay. What about vacuum mixing? This is something that we have not talked about, but the surgeon uses the syringe. So here you see the syringe. And what they don't want is that in the cement they have a lot of air bubbles, because it weakens the cement, right? So what they then do is they have a vacuum pump so that they can suck out all the air. So that's clear. So they get a really nice cement mantle flow, or cement flow. Because if you look at the cross-section, and this was a specimen, you can see sometimes big pores. Okay, and that weakens, of course, the cement. Okay, if we look at that Swedish register, they can find out that vacuum mixing doesn't matter. So Malchau is the author of the Swedish register. He says that vacuum mixing doesn't do anything. So to remove all the bubbles, it doesn't make any difference. So don't bother. It's expensive. It costs time in the operating theater. And Mr. Ling and Lee, they also said that their implants doing super well, even with extremely porous cement. Porous means with a lot of air bubbles. So there is no difference in clinical outcome. And as a mechanical engineer, I think, well, what's happening here? Because you have weakened your cement. And if we do tests, right, this is a computer simulation result, but if you do air bubbles in such a specimen, you know that the more bubbles, the weaker it's going to be. So what's going on? Okay, so if you look at it, this is, so we're looking now at a slab, yeah, at one cross section, and you're looking at this bit. So we have the implant here, and this is the cement. And we see the stresses in the cement. And we can see here a starting crack. So there's a stress intensity here, okay, around the corner of the stem. That's logical, huh? If we simulate pores in the, so we just simply had, let's say, removed elements, basically, there is hardly any difference in the stress pattern. So maybe the porosity is not so important after all. So this is a movie, and we have this crack propagation simulation, and we run it until 2 million loading cycles, and it just doesn't reach the end. It's almost cracking completely, but almost. So we should have run it until 3 million loading cycles. Okay, so this is a crack propagation. If we have a pore on the road, on the track of the crack, it will crack earlier at 700 loading cycles, 700,000 loading cycles. So at 2 million loading cycles, we didn't end up here, huh? But if there is a pore on the track, it's going to accelerate the cracking. And here you also see a pore on the crack pattern, on the crack track. After 1.7 million loading cycles, a complete crack. So if it is on the track, it is accelerating failure, because cement fails basically if it's completely cracking. If it's off the track, it is diverting the crack. So you could see here, if you compare this to this, the crack is not reaching as far after 2 million loading cycles as if there was no porosity. So sometimes porosity can lead to crack deviations, which is maybe even beneficial to prevent a complete crack. That is rather confusing, huh? If you have a pore even further, the crack is even shorter. So here you have 9% porosity, and the crack is hardly there because it's kind of deviated within the cement mantle. Yeah. So this is just an animation how the crack goes, because you can see at one stage it's also initiating from the crack, from the pore, of course. So when we did a lot of simulations, it turns out that I think if you would go on and increase the porosity, it will have an effect. But I can now understand why the effect is so clear in a tensile specimen and not so clear around an implant, because vacuum mixing has a relatively small effect, and the stress intensity of the stem, of the corner, is much more important than the pores. Okay, the last bit is about the cement-bone interface. So that's the interface between the cement and the bone. So I showed you this before, and I was proud that we could predict the cracks around the corners of the stem in the cement. Huh? If you look carefully at retrievals, this is a cross-sectional of a retrieval, the interface between the cement and the bone is very, very chaotic, because there is cement penetration in the bone, and it's not a straight line as here, right? So it's much more diffuse and complex from a biomechanical point of view. So this is absolutely not the same as this. So what we did is we took specimens of this complex interface. Yeah. So we made very small specimens, and the people in America did that, our collaborators. And they pulled them apart. Okay, so this is bone, and this is then cement. Okay, and we made micro CT scans of them, of these small specimens. These are 7 by 7 by 1 centimeter, so 7 millimeter by 7 millimeters, something like that. So it's very complex, this model, because it has a huge number of elements, and it is not a linear model because it has an interface. And you can see that the cement grabs hold of the bone because it's penetrated, and it's very complex. You can imagine that. And we could model the stiffness property. So this is stress and this is strain. And in the experiment and in the finite element simulations, we were able with our micro models to simulate it quite nicely. So if we then implemented the interface instead of this straight line, but more, let's say, a softer interface, things will change. So we did a simulation with this interface, with the old interface. We count the number of cracks, it's 300. If we simulate the realistic number of, the realistic interface behavior, we count double the amount of cracks. So this shows, this is an example that we have to assume a lot in these finite element models, but small changes can make a 2 times difference. So, but we are getting more and more realistic. Okay, this is my last slide. So we know that stems debond from the cement mantle. Polished stems may subside in the cement mantle, but perhaps produce less cement abrasion. So subsidence itself is not such a problem. We know that cement creeps and allows for some subsidence without cement failure. These Exeter stems, they were one of the best stems, and these are the polished stems, so they do very well. Cement stresses relaxate to some degree, and it's important to obtain a stiff and strong bone cement interface for the surgeon, so he has to pressurize the cement very well to get a stiff interface in order to protect the cement from failure, because otherwise we end up with a double number of cracks. Okay, thank you very much. Ja,